Cohn on Sunday amply demonstrated the fact that it's better to listen to him than it is to me speaking about him. So I'm going to do the same thing again today, just give you Professor Cohn, who today will explain a little bit further the intriguing relation between eigenvalues and zeros of the compensation function. Thank you.
All right, so let me remind you where I stopped essentially last time. What we had got was, you know, this exact sequence of Hilbert spaces. Okay, and I think the best model for that, I mean, you know, that you should have in mind, is the model where you take Riemann surface, sigma, and you take H0 to be the space of even forms. So even forms, I mean forms which are either 0 forms or 2 forms, okay, and which are orthogonal to harmonic forms. So this is a codimension 2 subspace inside the space of even forms. H1 is a space of odd forms. Okay, and the map here, which I was denoting by T, the map T is just equal to the Durham D plus its adjoint, this star. Okay, so we can keep this in mind. Now in our case, what we had a similar exact sequence. There was a delta, but let me ignore the delta for the time being, okay, because it's something that we shall get rid of. And the space H is this Pauli-Hilbert space. Okay, which is giving you the spectral realization of the zeros of all L functions. Now, when I talk about spectral realization, there was a delta, and the multiplicity of zeros were constrained by delta. Okay, and the zeros were also constrained very naturally to be on the critical line. Now, H1 is a very trivial space. It was just the L2 space of the Hidel class group CK, so there was delta, of course. And so, I mean, this space, in a sense, is, if you want, a white light, because when you look at the representation of the Hidel class group, everywhere, the space CK, I mean L2 of CK, if you want, every element of the group has 0 trace, obviously, except for the identity element, okay, because every element is just shifting. It has a matrix which is off diagonal. And H0 was L2 with the delta also of X, where X was the space of Adel classes, namely the quotient of the Adels by the multiplicative group of K. And now I can talk about this space. In fact, exactly as in the case of Riemann surfaces, we shouldn't get all of L2 delta of X, but we should get a codimension 2 subspace of it. And we can see that very readily for the following reason, that if you want to think about a function on this quotient, you see, in general, that's a general rule in non-commutative geometry, but I mean, it's an obvious rule, that if you look at a quotient space, which is tricky, in order to understand functions of the quotient, you should lift functions upstairs and look at them as functions on A, okay? So in fact, we are looking at the Schwarz space, the Brouillard-Schwarz space of functions on A. And also, we would like to arrange so that, if you want, the map which goes from H0 to H1, we would like this map to be isometric. I mean, you know, in the case of Riemann surfaces, this means that you take a Sobolev space instead of taking L2, and things are much better if you do that. Okay, so then we have absolutely no choice. If you take a function which belongs to Schwarz space, and you want to associate to it a function on the quotient, okay, what you have to do is clear. You have to take, if you want, the sum of the value of the function at the transformed of the points by the group K star, all right? And if you want this map to be isometric, if you remember that the R measure for the additive group is dx, whereas the R measure for the multiplicative group is d star x, and they are formally related by the relation dx equals absolute of x times d star x. I mean, this is true for a local field. When you look at the global case, it's a little bit more tricky, but very little more. And the homogeneity is the same. In fact, the correct equality in the global case is that dx is equal to the limit when epsilon goes to 0 of epsilon times this. Okay? So, I mean, the homogeneity is clear. It is the same. And it means that if you want the map E, the restriction map, to be an isometry, you should introduce an x to the 1/2 here. Okay, and this is what I will call E of f, evaluated at x. So I will now take this map, call it E. The map E is an isometry. So everything is well set up. And what you find immediately is that for this function, E of f, to be in L2, if you start with a Schwarz function, you precisely need two linear conditions. So that's why we get a codimension 2 subspace, exactly as in the case of Riemann surfaces. And the two conditions are the following. You need to have that f of 0 is equal to 0, otherwise that expression would be meaningless. Okay, I mean, you have to be careful about that. And the second condition is that integral of f dx has to be 0. I mean, it's easy to understand why, because when you consider these sums, they are Riemann sums for the integral. Okay, because you translate, you are on a lattice, and then when you let x go to 0, if this integral was not 0, you would get an obvious divergency, which would be far too strong. So you need these two linear conditions, and these two linear conditions are very similar to the fact that when you take a 0 form, it should be orthogonal to the constant 1. Okay, and that when you take a 2 form, it should be orthogonal to the volume form. Okay, so I mean, these are exactly similar conditions. Okay, but nevertheless, I mean, we have this sequence, and we have three representations. I mean, on H0, we have a representation U, which is the most obvious representation. You see, the ideal class group is acting like by diffeomorphisms. So the situation is very similar to a situation where you would have diffeomorphisms acting on a Riemann surface, not preserving the metric by any means, diffeomorphisms. And here we have this group of transformations, the multiplicative group, okay, which is acting obviously on the various spaces, and it's acting now. So I will write explicitly the three representations. I will call them U, V, and W. V is the obvious regular representation, so it's unitary if you want, and it's defined by the formula that V of G applied to a vector xi at a point x is just equal to xi of G inverse x. Okay? Now, U is the same representation, if you want. It's the action by diffeomorphism on functions. So it's written in the same way. So U of G times the function f, let us say, let's use a different letter, is just equal to f of G inverse x. But you see that there is a slight nuance, because since I put the x 1/2 to make the restriction map an isometry, what you find out is that it's not true that the map E commutes on the nose with U and G. What you have is that E times U of G is equal to absolute of G 1/2 times V of G times E. What is the reason for that? The reason is that you see V of G is isometric. But U of G is not isometric because it's not a diffeomorphism preserving the volume form. It's scaling. When you act by scaling, you don't preserve the additive R measure. You scale it by the module. Okay? And that's why you get this G to the 1/2. This G to the 1/2 is very important because it's the same 1/2 as in 1/2 plus IS for the zeros. Okay? This is a very important 1/2. And so its origin is really that why do you have to take square root? You have to take square root because you take Hilbert spaces. And this is where the 1/2 comes out. Okay? So you have this rule. And finally, there is a representation W, which is just the quotient. So W is just the quotient representation. See, what you find out, of course, is that by construction, the subspace H0 is invariant. Okay, so I mean, you can take the quotient representation. So you have the representation W. Now, what did I say last time? I mentioned the preliminary result. And this preliminary result has a corollary. So I won't write what it was, but I will just write the corollary. The corollary holds in all cases. And this corollary allows you to compute the trace of the representation W of G. This representation is traceable. Okay, it has an ordinary trace in Hilbert space. You can compute the trace. And what you find is the following formula, is that the trace of the integral of H of G, so H is a function on the ideal class group, times W of G times D star G. D star G is a normalized, suitably normalized R measure on the multiplicative group, on the del class group. So this is given by the following formula. It's given by the sum of the Fourier transform of H, evaluated on the Grossen character chi, and evaluated on rho, with the conditions that the L function associated to chi and to 1/2 plus rho vanishes, and with multiplicity, moreover, you want rho to be purely imaginary, rho belongs to IR, and moreover, the multiplicity is not the multiplicity as it of the 0, but it is the infimum of the multiplicity as 0, okay, and 1 plus delta over 2. All right, so what is the Fourier transform? Well, the Fourier transform is defined in the obvious way. H hat of a Grossen character and of Z, in general, is just given by the integral over the del class group of H of U, chi of U, absolute of U to the Z, times d star U. And of course, the normalization of the R measure in the Fourier transform has to be the same as the normalization of the R measure in the formula here. Okay? So that's a simple formula. I mean, the first, if you want, where things really begin is that, well, in this formula, this was the original motivation, but as we shall see, it has been improved very much, but the original motivation was the following, that here you have a natural way, not completely natural because of the delta, but you have a natural way to pick up only the zeros which are critical, which are on the critical line. Okay? Now, on the other hand, we can imitate the proof by Attia and Bott of the Lefschetz theorem. You see, if we go back to the case of Riemann surfaces, all right, when you have a diffeomorphism acting on Riemann surfaces, and you want to know what is the trace of the representation of the diffeomorphism acting on the cohomology, namely what I have written as H over there. There is a very nice formal way of doing it, which is due to Attia-Bott, and which is the following. So the Attia-Bott proof, if you want, of Lefschetz, of the Lefschetz formula, is the following. You see, you take a manifold sigma like here. Okay. Now, if you have a diffeomorphism of this manifold, take a diffeomorphism phi of the manifold, and assume that this diffeomorphism is generic enough that it is transverse to the diagonal. So, I mean, if you look at the square of the manifold and its diagonal, delta, then the graph of the diffeomorphism will look something like this. Okay, it won't be tangential to the diagonal. Okay, it will be transverse. Now, it might seem hard to compute the trace of the action of phi on the cohomology, but there is one thing that one can very easily do, which is to compute the trace under quotes of the following unitary operator, following operator, u sub phi, where u sub phi acting on a function f at x is just f of phi of x. All right. Why is that very easy to compute? You see, because when you have an operator, this is an operator acting on functions. Okay? When you have an operator, and this operator is given by a formula of the type Tf of x is equal to the integral of k of x y, f of y dy. Okay, if you take an operator which is given by such a formula, then the trace of the operator should be the integral of the diagonal values. I mean, you know, this is like for a matrix. If you have a matrix, the trace of the matrix is the integral of the diagonal values, the sum of the diagonal values. So the trace of that should be simply the integral of k of xx dx. Okay? So let's do that for this operator. This operator can be written as a kernel because f of phi of x is equal in local coordinate to integral of the delta function of y minus phi of x f of y dy. Okay, so you see that this is k of xy in local coordinates. Otherwise, I couldn't subtract y and phi of x. Okay, but you see that in local coordinates, I can write a kernel, k of xy. Otherwise, you have to use invariant distribution theorem. So this is nothing. And so you have a kernel, k of xy. And now the trace should be the integral of the diagonal values of the kernel. Now the diagonal values of the kernel, this is just x minus phi of x. So in fact, what you have to compute is integral, so take a fixed point, and compute integral of delta of x minus phi of x dx near the fixed point. Okay? Now, near the fixed point, you can use local coordinates, and you can change variables so that x minus phi of x is approximated by 1 minus phi prime applied to x locally. So you can change variable by this change variable. Okay, and what do you get? You get that this is obviously equal to 1 over 1 minus phi prime of x0. And when I write absolute value, I mean the absolute value of the determinant. Okay, I mean this is obvious. Now, you can sum over all fixed points, and what do you get? You get that the sum, that this trace, if you want, is given by the sum over all fixed points, so phi of x equals x, of 1 over 1 minus phi prime of x. Now, if you apply the same formula not only for 0 forms, but also for 2 forms, and you subtract what you have for 1 form, you get immediately the Lefschetz formula. I mean, this is explained at the above. There is a point which has to be justified, which is that this trace is not an ordinary operator trace, because it's a distribution theoretic trace. Okay? So what you have to justify is that when you make the suitable difference of traces, you do get the operator theoretic trace. That takes a little bit of justification. As we shall see, I mean, this will be a very important point for what we are doing. Now, this immediately extends to flows. So this has been extended by Guillemin and Sternberg. I've extended, if you want, this discussion about Diabot to flows. By flows, I mean the following. I mean that now I am no longer considering a single transformation, phi, but I am considering a flow, okay, a one-parameter family of transformation, forming a group, phi sub t, if you want, or f sub t, all right, which, let us say, is the exponential of a vector field, v, on the manifold. And what you find out when you compute the same expression, or rather when you compute, you have to smear things, so when you compute, if you want, a trace of now the integral of h of t, u of t, dt, where u of t applied to a vector psi at x is nothing but psi of ft of x. All right? So you see, when you compute that, you can do exactly the same computation, and without any surprise, of course, it will be given by contributions of fixed points of the flow. But fixed points of the flow can be of 2 kinds. Because when you have a flow, you can have, the first thing that you can have is a fixed point that, like ft0 of x is equal to x. That's a periodic orbit of length t0. That's the first kind of fixed point. But you can also have a flow, you know, like the homothéties on R, I mean the dilations on R, which have a fixed point here, which is not a periodic orbit, which is just a single point. Now, it turns out that there is a very nice way to unify what you get for this and what you get for that. And this is the following. So the formula is the following, is that the trace of the integral for a flow of h of t, ut, dt is equal to the sum. Now the sum will comprise all sorts of fixed points, namely either the periodic orbits or the absolutely fixed points. So it will be a sum, if you want, over these things. And for each of them, you will have an integral. That integral could be a discrete sum when the isotropy is discrete, but it will be an integral over the isotropy group of any given point of the corresponding fixed set, okay, like a point here or this point. Doesn't matter which point you take, the isotropy is the same because everything is abelian. And then what you have is an integral of h of t over 1 minus the Poincaré return map, absolute value, because I take determinant, and then I write d star t, which is the R measure on the isotropy group, which is of covolume 1 with respect to this R measure. All right? If you look at the various formulas, okay, I mean, when you look in books, for instance, you'll find formulas where you have the order, if you want, the period in the formula. But if I multiply the counting measure by the period, I get a measure which is of covolume 1. Okay, so this is the correct normalization. So this star t is of covolume 1. in the B group. Okay, so that's the formula. All right, so I mean, really the point of departure of my work on this problem was the following. The point of departure, I mean, it was not this theorem, it was found later. So the point of departure was the following, was that if you look at the space, if you take your space X, which is the space of Adel classes, A mod K star, space of Adel classes. Okay, and if you act on this space by the scaling group, okay, so act there, act on X by the group CK. Well, as I said very early last time, you can compute the fixed points and so on. You can make the zoology of fixed points. All right? So you can do exactly that computation, except that it is not R, the group which you are dealing with, okay, but it's a group which is commensurate to R plus star. Of course, R plus star is isomorphic to R, the group. But it's a group which is slightly a little bit more involved because it has a compact piece, but that's nothing. And so the formula that you get, you see, the formula for the trace, but still a trace under quotes because it's that distribution theoretic type of trace of the integral of h of g, and now I really write u of g. Okay, I really write u of g in the sense of my representations. So I am just permuting the points of the space. Okay? So in other words, I am just computing the trace of a permutation matrix. The space is, of course, not a finite set. Otherwise, this would be trivial. Okay, so trace of integral of h of g, u of g, d star g. D star g is R measure on the ideal class group. Okay, when you compute it, what do you find? You find a sum over all the periodic orbits. And when you compute, you find that they are labeled by the places of the field. In other words, by the primes. So it's a sum over the places, sigma over v. And then you have an integral, exactly as you have there. You compute the isotropy, and what do you find? You find that the isotropy groups are the local fields, k star sub v, completed with respect to the place, but the multiplicative group of the local fields. Now, these are subgroups of the ideal class groups, and the way they are subgroups of the ideal class groups is exactly the way by which the local class field theory relates to the global class field theory. Okay? This is the group for global class field, for local class field theory. This is the group for global class field theory. They are related to each other, and that's what you find. You find the same inclusion. Now, what do you find? You find h of u inverse. There is an inverse because there is a discrepancy in my notations, because I was using psi of phi of x here, f of phi of x, whereas I was using g inverse over there. Okay, I mean, it's very important to be 10 times careful. Then there is the local module with respect to the place v of 1 minus u, which appears. How does it appear? This is not surprising. It just appears like this. Okay? And finally, you have a certain multiplicative R measure on the multiplicative group of the local field. But if you take the veil normalization of R measures for modulated groups, you'll find that it fits exactly on the nose. That means that the normalization of veil tells you that this R measure is of covolume 1 in the big R measure. Okay? So this is what you find. Okay, now what do we know from André Veil? We know a very beautiful result, which André Veil found, I think, in the 50s. So there is a theorem of André Veil, which tells you the following. Okay, which tells you that this sum is well known in number theory. The sum over V of integral over these local fields, K star B, of a function on the ideal class group, divided by 1 minus u, V star u. Okay, André Veil had to introduce some very specific finite values, but I won't mention it. I mean, let me assume that h of 1 is 0 for the time being. So I don't need these finite values. In this case, the integral is well defined. So that sum, what does André Veil tell you? This sum is equal to the Fourier transform of h at 0 plus the Fourier transform of h at 1 minus the sum over all zeros and all constant character of the Fourier transform of h at chi and rho. Okay, and now there is no restriction on the fact that the zeros have real part 1/2. It is all zeros, and the multiplicities are the maximal multiplicities. So you see, I mean, this was very early observation, and what did it mean? It meant that if you now compare, well, notice that the minus sign which is here is the same as the minus sign which was occurring from the very start. Okay. Now, let us compute formally using the trace, the character of the representation W. Let us compute formally in the same way the character of the representation U. You see? Now, remember that we had to impose two linear conditions which are here. Okay? When we were looking at the space. So if we reintroduce these two linear conditions, in fact they correspond to two representations of the ideal class group. There is a trivial representation here, so this is a trivial representation. Okay, and this is what is called the Tate twist. So this is called C if you want. And this is called C of 1. This is a Tate twist of the trivial representation. I mean, but it's a very trivial fact that if you take this condition and you act by the scaling group, you will multiply this condition by the module. Okay? So this will give you two terms. It will give you this H hat of 0, and it will give you this H hat of 1. All right? But now why do you get this minus and this sum over here? Why do you get this minus? Well, it's extremely simple, because when you look at this exact sequence of representations, all right, the representation H1, as I said, is a regular representation. So the trace for a function which vanishes at the identity, the trace is 0. Okay? So what do you get from this? You get that the trace of U is the opposite of the trace of W. All right? But there is a shift of 1/2 which comes from this equality. Okay, and this shift of 1/2 changes in this formula the fact that I had H hat of chi and rho with L of chi 1/2 plus rho is equal to 0. Now the 1/2 is reintroduced. Okay, and you get exactly the same as in the Weil formula. Okay? So you see, I mean, this was the original motivation. And the original motivation was that somehow, if that was not formal, namely if one could do exactly the same step as Atiyah and Bott did when they justified the Lefschetz formula, not, you know, by a rigorous classification, then one would be finished. Because you would have an equality between the sum over all zeros and the sum over critical zeros. However, there was a big difficulty, which now is overcome for that, which was, if you want, that there was no natural value of delta. You see, there is this parameter delta, which is very unpleasant, okay, and which was there in order to be sure that, I mean, that you can see these zeros in the quotient representation. It's some sort of regularity condition. But there is no natural value of delta. There is no preferred value of delta. And so this was quite a serious problem. And I mean, of course, you know, the natural thing to do in front of such problem is to try to proceed and actually prove, justify the formulas. Okay, and so I mean, the first justification that I will show, I will start with the local case. You see, the point is that when Gilman, Sternberg, or Atiyah and Bott, and so on, consider trace formulas, these trace formulas are distribution theoretic. And the traces that you obtain, I always put quotes around these traces because they are formal. Now, what you want really is to have traces which are operator theoretic traces. Now, we know a perfect case where this is done, and this is the Zellberg trace formula. Because Zellberg had a very similar problem in his trace formula, and the problem in the case of Zellberg came from the following. You see, in the case of Zellberg, everything would have been easy if the manifold, the Riemann surface that he was dealing with, had been compact. But it is not compact, and it has a cusp. I mean, you know, it has something like an infinite cusp, like this. And because of this infinite cusp, what happens is that he has exactly the same problem of the white light as I have here, except that in this case it's an emission spectrum rather than an absorption spectrum, so it's easier. So what did he do? Well, what Zellberg did was to introduce what one calls in physics a cutoff, namely to say, you see, the reason why the trace is divergent, why you don't have a trace class operator, is because the space is infinite, and in physics terms, I mean, what you have to do is what is called an infrared cutoff, namely cut the space, and then everything will converge, everything will be trace class, and so on and so forth. So what Zellberg did, he introduced some regularization, R lambda, okay, which is if you want, the orthogonal projection on the subspace of the Riemann surface, and then he made all the computations in the localized case, and then he found that if you remove this cutoff, and if you look at whatever operator you want to look at, okay, x, if you want, then the trace will not converge, but it will behave like a logarithm of lambda times some constant plus a finite term. And by identifying the finite terms, both from the spectral point of view and from the trace space computation, he was able to prove the Selberg trace formula. Okay? Now we shall see that the situation is exactly identical in our case. Okay? And, but let me begin by the local case. There are a few subtleties. Okay? There is one thing which is a little more tricky. So let me start with the local case. I mean, the local case cannot be simpler. It's something which is, at least if you so local case, I mean, I take a field K, which is a local field. But I mean, if you don't know about local fields, what you can have in mind is the field K equals R, the real line. Okay, I mean, so you can keep in mind if you want the field which is R. Okay, and so in that case, I mean, R is a very nice manifold. Okay, and I mean, the flows that we have in that case. So I mean, in general, I will consider, if you want, the action of the multiplicative group K cross acting by multiplication on K. See, I mean, there is hardly anything simpler. But if we take the case of the real line, that means that if I wanted to talk in terms of flows, I will consider the flow Fs of t is equal to e to the s times t. All right? I mean, this is a flow on the line. This is an obvious flow on the line, okay, which is given by the vector field, which is x d by dx. And this flow has one and only one fixed point, which is the point 0. So we know what is the formula, which is given by Gimer-Sternberg. Okay, this formula is just integral for the trace. It's just integral of h of s, sorry, over 1 minus e to the s, absolute value, ds. Okay, this is the formula for the trace. All right. Now what we need to do is not to have this formula just as a distribution theoretic formula, but really to have it as an operator formula with good traces in Hilbert space and so on and so forth. Okay, and what is the theorem? The theorem is completely general. It is by no means restricted to the case of the real line. I mean, it holds for any local field. So this is the first sort of rigorous. Of course, last time I wrote the theorem about the spectral realization. That's also sort of completely rigorous result. But let me write the second completely rigorous result, so which is the following. So the theorem is the following. Theorem is, so let K be a local field. Local field. Okay, and you act by K cross on K. So in fact, you act on, of course, on L2 of K. When I talk about L2 of K, I'm talking about L2 with the standard R measure, of course. Okay? And you act by scaling. That's all. Okay, now I will write a Selberg trace formula for that case. Okay? I mean, so the formula is the following, is that the trace of R lambda times U, I call U this representation, U of H is equal to 2H of 1 times log prime lambda. I will define what is log prime lambda, plus the integral of H of U inverse, exactly what we need to have, over 1 minus U, the module in the local field, times d star U, and I will put a prime here and explain what it is. Now, what is, so there are two primes plus little o of 1. Okay, in fact, this little o of 1, it's a big O of any inverse power of lambda. Okay, now what is R lambda? R lambda is the cutoff, like in Selberg, but it's a little bit more tricky than in Selberg, because R lambda, you see, at first you would think you just have to do as in Selberg, namely, the field is infinite. So let's cut off by going from minus lambda to lambda, or for an arbitrary field, you cut off where the module of x is less or equal to lambda. Okay, this is a compact piece of the field. Okay, but that's not enough. And that's not enough because the situation is entirely symmetrical between momentum space and the position space. So you also have to cut off in Fourier. Okay, so the correct cutoff, if you want, is not only what physicists call an infrared cutoff, which is what I have here, but you also have to perform what one calls an ultraviolet cutoff. Okay, and you perform this by following. So this projection, I will call it P lambda. It's obvious. Okay, I mean, it's projection on the L2 subspace of functions which are localized here. But you have to cut off by P lambda hat times P lambda, where P lambda hat is the Fourier transform of P lambda. Okay, and notice that this depends on the basic character that you take, because it depends on the Fourier transform. All right. Now, what is log prime of lambda? You see, when you take a P field, if you take a field which is not Archimedean, then the module of the field is powers of some number q. And so it will not be the log, but it will be, in fact, if you want, the term 2 log prime of lambda, that will be equal to the integral from for modulus of x less than lambda, but bigger than lambda inverse of d star x. Okay? All right? Of course, in the case of R or C and so on, it gives you 2 log lambda. But, and of course, in general, it's equivalent to 2 log lambda, but this is what it is. And finally, there is this subtlety here. Okay, and this subtlety here is related to some previous work of Shai. And I mean, it's related to the, well-known fact that when you take this distribution, when you Fourier transform it, you get logarithm. Okay? But here, it turns out that by a miracle, you get that the normalization of the finite value, because that holds for any function, even if it doesn't vanish at 1, the normalization of the finite value is exactly prescribed, as in physics, by the fact that the Fourier transform, the additive Fourier transform of a suitable distribution here, vanishes at 1. And you notice that, you see, it's covariant with respect to the choice of Fourier transform, exactly as this is covariant with respect to the choice of Fourier transform. Okay, I mean, this is not difficult to prove. It's an easy exercise. But it is extremely satisfactory in the sense that it gives you a model. Even, you see, the local case is always very easy in number theory. But it gives you a model of what one should do in general. Okay? Now, and this is proved. Now, let me write a semi-local case, okay, which is, there is one thing which I forgot to say while I'm erasing the blackboard. See, there is one thing which is extremely striking when you look at the formula of André Weil, which is over there, which is that if you look at this formula of André Weil and take a function h, which vanishes at the point 1, okay? So you don't need any finite value and so on. Now, the left-hand side has an amazing property. This should have been noticed many years ago, but the left-hand side has the following property, that if the function is naively positive, then the left-hand side is positive. Now, you see, this is very important because it tells you that the representation you should look for as is what I will call Hadamard positivity. You know, Hadamard defined a matrix and product of matrices and so on. So I call Hadamard positivity the fact that matrix elements are positive. Now, this was telling very strongly that the representation one is looking for should be not obtained by quantization, but should be obtained simply by permutation matrices. Because it's only permutation matrices which have a positive trace. Okay? And you see here what you have. You have a function, a distribution, which has this property. And because it's realized by permutation matrices, of course, the Gilman-Sternberg formula and so on also has the same property. Now, what one can do is go one step further from the local case. And you see, because this local case is very easy, because the space on which you're acting, the space which replaces the Adel class space. So this what replaces A mod K star. In that case, in the local case, this space is very simple. It's just a field K. Now, this is an ordinary space. As I said, it's a manifold for the case of R. You can also work out the case of complex numbers. It's also a manifold. You also have a flow. You can work it out and so on. I mean, the case of periodic numbers is nothing hard. But you see, you have an ordinary space. So in fact, if we want to have some confidence, we should treat a case when we don't have an ordinary space. Now, this is very easily reached because this Adel class space can be, you see, you have a local model not when you take one place, but when you take finitely many places. So let K be a global field now. be global. So take a global field, and let S be a finite set of places, but which contains all infinite places. Okay? So for instance, you could take k equals q of square root of 2, okay, and you could take the two infinite places. All right? So now I will describe to you what is the local model in that case for a finite set of places. What do you take? What replaces the space of Adel classes? Well, we know very well what replaces the ideal class group. This comes from Dirichlet's theorem. So the ideal class group has a very clear representative. It's approximated, in fact. It's approximated by the following group, which is a product of the multiplicative groups for V in the finite set of places, okay, divided by a discrete group which is called the group of S units. Now, what are S units? They are elements of the multiplicative group of the field, which are of norm 1 for every other place, which is not S in S. Okay? So what would it be in this case? This would be the group of units of the field. Okay? Namely, it would be elements of the form A plus B square root of 2. Okay? But for instance, 1 plus square root of 2 or elements of this type, so that they are units. Okay? Okay. So now, what replaces, but this is a very easy group. This is still a group which is commensurate. This is still a modulated group, if you want. Still modulated group. Namely, this group is commensurate to R plus star. Okay? This is Dirichlet's theorem, essentially, which tells you that. Right. So it's essentially CK. You see, if you take S big enough, then the group of ideal classes is in fact the product by all elements which have norm 1 everywhere, essentially. Okay, so this is what replaces the ideal class group. So what replaces the space X? Well, it's very easy. You just take X sub S now, which is the product of the local field, not the multiplicative group, but the local field. And you divide this by OS star. That's your space. So what does it look like? Let's look at the case of Q of square root of 2. Okay, you see what happens in the case of Q of square root of 2, which is that the units, they act in an hyperbolic way by hyperbolic transformations on each of these quadrants. So when you divide by them, you get the group itself, this first, okay? And then you get a nice circle, because when you divide this axis by the action of the group, you just get a circle. When you divide this side, you also get another circle, okay? And then you get the point 0. So this space consists of a generic orbit, which is just the action of the group, of an orbit which corresponds exactly to the orbit of the Frobenius when you consider a curve, another orbit of Frobenius when you consider the curve. So it begins to imitate the curve. And finally this point. And they are glued together in a very tricky way. Okay? Now, you can consider a slightly more involved case, which is very interesting, well, for instance, you can take k equals rational numbers, okay? And now you can consider the set of places which is 2, 3, and infinity. The three places which are from the prime 2, the prime 3, and the prime infinity. What will you get? You'll get the two adic numbers, Q2, cross the three adic numbers, Q3, cross the real line, and they will be divided by the groups of powers of 2 and 3, plus or minus powers of 2 and 3. Okay? Now you can see that because I took three places, I have really a non-commutative space here. It's a very tricky space because the action of powers of 2 and 3 on R, for instance, is ergodic. Okay? It's a very non-trivial action. So you see that as soon as you take more than two places, you have the same type of difficulty as you have for the global case. All right. Nevertheless, here is a proven theorem, which is the following. Okay, so you see, what is extremely important, of course, is to be able to justify things in situations which are analogous. Now, the situation which is analogous, which I have described here, is a situation where the Adel class space, which at first, of course, globally is very hard to comprehend, has been replaced by what happens over finitely many places. But you see, it's not a big difference, because when you consider functions on this Adel class space, essentially these functions leave any function will live on one of these finite approximations. So I mean the situation is quite well approximated by the description which I gave there. Exactly as when you consider functions on an infinite product of spaces, they are approximated very well by functions which only live on a finite product. Okay? So in fact, the theorem is the following. It's the exact analog of the theorem over there. Okay, so the theorem is the following. So let K be global now. Okay, and let S be a finite set of places. Finite set of places. Okay, and let us consider the reduced ideal class group CS, the reduced ideal class space, which is XS. Of course, CS is acting on XS. So CS, if you want, acts now on L2 of XS. And there is no delta. Notice that there is no delta here. Okay? Now, the theorem, there is one thing which is non-trivial, even to state the theorem, which is that I have to write down this product P lambda at. Okay? Now, P lambda is very easy to write down. You see, so let P lambda be the orthogonal projection. Let P lambda equals orthogonal projection on the subspace, which is given by the functions, if you want xi, with xi of x equals 0 for any x such that modulus of x is bigger than lambda. This is quite easy to define, because modulus is well defined on XS, because the group of local units is actually of modulus 1. Okay? So this is well defined. However, if you want to define P lambda, you need Fourier transform. And it's a non-trivial theorem that Fourier transform exists. Okay? Namely that when you consider Fourier transform on the product of the KV here, it passes to the quotient. I mean, it defines an isometry on the quotient space. That's a non-trivial result. Okay? It's also a non-trivial result that on L2 of XS, you don't need these two linear conditions I was talking about, no longer. That's a tricky theorem, but you see, because now you don't have a Riemann sums, because the local units, the S units, do not form a lattice. They form a very sparse subspace, and you can prove that the function, when you sum them, they have a logarithmic growth when they go to 0. So you don't need these linear conditions. Okay? But this is an estimate, which is tricky. But L2 of x is well defined, Fourier transform is well defined, and so let P lambda at now be Fourier composed with P lambda, composed with Fourier inverse. Now it makes sense because Fourier makes sense. And as I said, this is a non-trivial result. Now the theorem is exactly the same as here, but you'll see the beauty is the following. The beauty is that you put R lambda is P lambda at P lambda, the same. Okay, you put U of H, exactly same formula, of course. It's equal to 2 log prime lambda, the same log prime, of course, times H of 1, as in Zellberg, there is no problem. But then, the beauty is that now it's a sum over places, okay, of the integrals, integral prime, and you have the same isotropy as we had hoped for, K star V, and you have H of U inverse over 1 minus U this time, plus little o of 1. Now, why I'm so happy about this thing? There are several reasons. You see, the first reason is the following, is that you could have been extremely worried in the global case, because I told you about the computation of the periodic orbits and so on. But 0 is a fixed point. Why didn't I count it? 0 in the ideal class space is a fixed point. Now, before I had only a very sort of heuristic reason why not to count it, and the reason was the following, that 0 is not an ordinary point, it's a singular point. It's an orbifold point, because it's divided, because the group K cross by which you divide is dividing it. So as an orbifold point, you should divide by the order of the orbifold point when you count the Lefschetz formula. And the order is infinite. So if you divide something by infinity, you should get 0, except if what you are dividing by is infinity also. Okay? Now, I began doing, very long ago, I began to do computations with these 3 places and so on. And I found that what you are dividing is finite, okay, by some geometric series and so on. Now, this theorem contains much more. It tells you that multiple places don't contribute. And it tells you that, very amazingly, even though the space that you are considering is roughly speaking a product, You see, this space, you could think of this space as being a product over places. So you would be totally misled because you would say, well, if I compute a trace in a product, it should be the product of the traces. Okay? So how can it be that instead we obtain the sum? All right? And the reason why you obtain the sum is because you are dividing by the group of S units, and essentially dividing by this group is like passing to a primitive part. Okay? So there is, I mean, a very, very strange and strong fact which can be seen concretely in all these examples, but which is saying, if you want, that even though that space, a space of Adel classes, would at first sight seem to be a space which is wrong because it's like a product. In fact, it behaves like a sum. And if you take glasses and you look at this space, okay, it's a non-commutative space. If you look at it, what you will see? Okay, you will see something like this. You will see the generic orbit. You will see as a cylinder, as I said. You will see the generic orbit of CK. Okay? As I said before, you see, when I was considering Q of square root of 2, if you take elements whose two components are non-zero, this is the generic orbit of the ideal class group. Okay? So you have this. And then, what you find is that you have a union of circles. And these circles have increasing lengths, which are like the log P. Okay? And they are glued together. There is a point 0, and the rest is a little bit of non-commutative glue. Okay, of course, it should be there. Now, if you think in number theory, if you think in the framework of André Weil and so on, of curves, what is the curve? What are the points of the curve over the algebraic closure of the constant field, over FQ bar? The points of the curve are each of them sitting over a place, and over that place, they are just the orbit of the Frobenius, which has the right order. Okay? This is exactly the picture that we get here. So this space, even though it would look at first sight to be a product, not at all. It's really a union of circles, which have the right length, but they have the right structure. You see, in algebraic geometry, the structure is coming from the coordinate ring. Exactly in the same way here, what we have is a space which has the corresponding structure. Okay, so that theorem is proven, and it has one immediate corollary, which is the following, which is that, look for something which, yes. Yeah. You see, then you can begin to analyze things, and what you find is that you should first consider the case of a non-zero characteristic. So if you take the case of characteristic a positive first, then what you find out is very strange. You find out that in fact you immediately have a corresponding cohomology. And the reason is the following. The reason is that if you look at the projection P lambda and P lambda at, okay, on a given, for a given Grossen character, so you localize on a given Grossen character chi, they commute. They commute for lambda large. They commute for lambda large. Okay? This is what you find by computation. And what does it mean? It means that the orthogonal, that the operator R lambda, which is P lambda at P lambda, in fact, this is the orthogonal projection on the intersection of P lambda with P lambda at, on the intersection of these two subspaces. Now, what is the intersection of these two subspaces? It's very simple. It is just functions which belong to short space, A. Of course, then you have to divide by quotient, you see. Functions in short space, which are such that the support, that f of x is equal to 0 for any x with modulus of x bigger than lambda. And Fourier transform has the same property. Okay? Okay, now this space is very easy to define globally, not only locally. And we shall call it Q lambda. Now, in the case of positive characteristics, for global fields of positive characteristics, there are plenty of such functions. You see, for instance, if you take the characteristic function of the maximal compact subring, its Fourier transform is also up to scaling the characteristic function of the maximal compact subring. So it has this property. So this space is very rich, okay? And now, what do you find out? So this is really the key result, okay? Now you can write down the same formula. Of course, it implies, because R lambda is now the orthogonal projection on this subspace. So I can replace R lambda in this formula by Q lambda. Okay? Then I get a true result. Okay? But now I can formulate the result for, not for finitely many places. Okay? It's global. Okay, now what is the second theorem? So, second theorem is the following. Is that now let's not take a finite set of places, let K be global. Let us first take a positive characteristic. Okay? And look at trace of Q lambda times U of H. Okay? And expand it. I mean, it's not difficult to prove that it has an asymptotic expansion of this form. Okay? Plus sigma of V integral prime over K star V of H of U inverse over 1 minus U D star U plus little of 1. Now, I cannot prove this. If I could prove this, it would be finished. But what I can prove is the following, is that if this formula holds, then the Weil distribution is positive definite. And that's what I will show you. Okay? Namely, that this formula implies, in fact it's equivalent to, that's not difficult to say, okay, implies that the Weil distribution, so that Weil of H star star H is positive. And of course this implies Riemann hypothesis for all L functions. Okay? So, you see, I will give you this proof, and I think it is the first proof of positivity of the Weil distribution, I mean, over complex numbers and so on. So let me show you what it's due to, because the argument is quite nice. And then I will explain what remains to be justified to prove the Zellberg trace formula. Of course, this equality, I call it the Zellberg trace formula for obvious reasons. Okay? I mean, it's not a fantasy in the sense that if I take finitely many places, I can prove it. Okay? And as I said, when you take functions, when you look at their trace, it's perfectly well approximated by what happens over finitely many places. Now, let me show you the proof of the Weil positivity, because that's really the key. You have to remember one thing, which is very, very confusing when people were dealing with the Weil distribution, which is that, which I just raised, that when you want to prove the Weil distribution is positive definite, it's extremely annoying, because there is a global minus sign. You see, the Weil distributions that you want to prove to be positive, what is it? It's W of H equals H hat of 0, essentially, plus H hat of 1. So far so good, this is positive. Minus the sum over all plates of integral prime over K star V of H of U inverse over 1 minus U D star U. In other words, the Hadamard positivity is opposite to the Weil positivity. Okay? See, this looks totally crazy. Okay. So what is the proof if you assume the Zellberg trace formula? Okay? What is the proof? The proof is the following. So in particular, you have to get the minus sign, and you have to prove that this minus sign is positive. Okay, that what you get from the minus sign is positive. What do? You prove that the projection Q lambda is smaller or equal to the projection S lambda. You see, I take the projection Q lambda, and I look at it indeed L. So this is in L2 of CK. And what is this projection S lambda? It is a projection on the functions which have support between lambda inverse and lambda. I hope it's clear what I mean. I am on the Idel class group, and I take G with modulus of G less than lambda and bigger than lambda inverse. Okay? Now, it turns out that by using Poisson summation plus vanishing, which is exactly the proof of Riemann-Roch, because Riemann-Roch theorem uses Poisson and the, vanishing, you prove the inequality of these two projections. You prove that Q lambda has an orthogonal projection in Hilbert space for which lambda is smaller than S lambda. Okay? What do you deduce from it? You deduce that trace of S lambda minus Q lambda times any positive operator is positive. This is elementary Hilbert space theory. And here I can put U of H star star H. Okay? Okay? Now, using the Selberg trace formula, what you see immediately is that the limit when lambda goes to infinity of this trace, you see I can compute the limit when lambda goes to infinity of trace of q lambda times this. This is a Selberg trace formula. There will be minus sign. What about the limit of trace of s lambda times this? This is a trivial computation in the regular representation. S lambda times this gives me exactly 2 log lambda, log prime lambda times h of 1. So the term which is 2 log lambda times h of 1, and this term cancels off. It cancels out. And I get minus this term. Okay? Of course, I didn't tell you about h hat 0, h hat 1, but they appear trivially. Okay? And so what you get here, you get that this is equal to the Veil distribution, W of h star star h. Okay? So what do you prove? You prove that the Veil distribution is a weak limit of positive definite functions. So it is positive definite. Okay? Now, this has been extended. I have extended this result from the case of positive characteristic to the case of zero characteristic, but it involves a completely new and beautiful landscape in mathematics for the following reason, which is that you have no function of a real parameter, for instance, which is with support in the interval minus lambda lambda, and whose Fourier transform has support in a minus lambda lambda. Okay, we all know that. This is Palais-Wiener or whatever. Okay? Now it turns out, however, that this situation was extremely confusing to people in signal transmission in 1960 or the end of the 50s. Okay? And this problem was resolved by people in Bell Laboratory. And their motivation was very simple. They didn't have a compact disc, but they had vinyl disc records. Okay? And they were puzzled by the following fact that if you take such record, I mean, obviously it has a finite length in time. So the signal function, starts at some time and stops at another time. Okay? But obviously, I mean, the frequencies which are involved in the signal are also bounded. Because if you look at music or whatever, I think there is a certain number of kilocycles beyond which it's 0. Okay, so what did they do? They found that, you see, you can look at these two projections, P lambda and P lambda hat, exactly the same as the one I have, P lambda and P lambda hat. Now, they proved that this pair of projections miraculously commutes with the second order differential operator on the line, H lambda, which is minus d by dx times lambda square minus x square times d by dx plus lambda square x square, essentially. Okay, so the two projections commute with this second order differential operator. Moreover, this second order differential operator comes from three-dimensional Helmholtz wave equation by one of the few coordinate systems which are separable, which are called the elliptic prolate coordinates. Okay, and I mean, they are a generalization of the polar coordinates, but by means of confocal ellipsoids in 3 space. And so a lot is known about this operator. All its eigenvalues are completely studied. They are generalization of the Mathieu equation, and there are fantastically beautiful mathematics connected to it. And what they provide you with, they provide you with a correct replacement of the intersection of these two subspaces. What it tells you is that these two subspaces essentially form a zero angle, and then they are almost orthogonal. Okay? Now, using this in my recent paper, I actually computed the dimension, so if you want, of the corresponding finite dimensional space and so on, and I found the Riemann formula E over 2 pi log of E over 2 pi minus 1 plus 7, 8, and so on. So in fact, this provides a finite dimensional space with a matrix which approximates the zeros of the Riemann zeta function. And this space, you compute its dimension by a computation of quantum mechanics, of quantum mechanical nature. I mean, I don't have time to explain it, but what I'm saying is that if you want, so to conclude, I would say that, when I had written this third column in my first talk, now the first line, which was interpretation of all zeros, what you find is that there is a certain cohomology which is obtained by looking at the filtration by this space P lambda, which will give all zeros and which I call adelic cohomology. Okay, I mean, the reason why I call it adelic cohomology is just to have a little laugh, because in the case of curves, you call it L-adic cohomology. Okay, so on that adelic cohomology, it's very easy to see that the action of what replaces the Frobenius as all zeros as eigenvalues and so on. Okay, then you have the interpretation of the Weil explicit formulas. It is the Lefschetz formula. Okay, and then you ask, what about the Riemann hypothesis? What is it? It's exactly this Zellberg trace formula. Okay, so I mean, justifying this formula, which is certainly fantastically hard work, if you want, but which is an equality now. Okay, justifying this formula, and which is justified. So I mean, for finally many places, which is very reassuring. It tells you that you won't have big surprises. So justifying this equality actually proves the Weil positivity. And you see, when you compute the spectral side, I just want to finish on that. When you compute the spectral side, you find that, unlike what I had written before, where only the zeros which were critical were contributing, there is something very beautiful which happens, which is that in case you would have a non-critical zero, it doesn't contribute to the explicit formula by its value, but it contributes by the Poisson potential that it creates on the critical line. That's what you find. So when you compute the spectral side of the Zellberg trace formula, you find that non-critical zeros, if they exist, provide you what physicists call a resonance. Namely, they don't contribute by their value, but they contribute by a positive definite function. And that's why Weil positivity is restored. Okay, so they contribute by their Poisson potential according to the line, to the critical line. Okay, but nevertheless, so if you want, it's what I know from gut feeling is that this formula where you replace the contribution by the value by the Poisson potential, of course, there will be a formula for this. Now the issue is this formula exactly the Weil formula? Okay? And all indications, of course, is that it is a Weil formula. If you can prove that it is a Weil formula, you're through. Okay? So you see there are plenty of, but obviously, I mean, you know, it's an extremely slippery territory, the territory which remains, and it's absolutely unclear what is the distance to the result. I mean, this is absolutely unclear, except that there is now this completely geometrical framework which is present. Okay, and that's very pleasant because it allows the mind to move. You know, you're not stuck. Okay, so I think I will stop. I should ask some questions, otherwise I feel bad.
Well, before you started with this problem, you thought that non-commutative geometry should be done via an algebra.
Right.
And the algebra here should be K-star.
Sure. Exactly. Exactly. Yes.
And how would that?
Yeah, sure. I mean, you know, I mean, this indeed, I will explain what is non-commutative geometry next time. I mean, this example is, I would say, probably the best motivation for non-commutative geometry, in the sense that you see, I mean, the reason perhaps why Tate didn't think about this and so on, is that people were frightened by this space of Adel classes. I mean, it's a very frightening space, okay? And so it is very reassuring that, of course, when you work, I mean, you find the zeros come out, you find that the right formulas come out, I mean, with all the right normalization and so on. But what we need is more. We need a full theory, and we need to develop a full theory without any preconceived idea. Now, it turns out that non-commutative geometry has been developed at the level of algebra. And namely that what has been done, if you want, is to understand all the properties like K-theory, all the properties of the spaces at the level of the algebra. Now, in a sense, what one would like, indeed, is when you want to justify this formula, and in fact, it's enough to justify it for the Frobenius. You don't need to justify, you no longer have problem when H, I can prove this formula when H is localized on the ideal classes of modulus 1. So, I mean, the real problem is for the Frobenius itself, for a single transformation. Now, when you look at that, you don't have problem with transversality. You have the Hadamard positivity which is present and so on. But obviously, it's a global question, and it's clearly a global question of ergodic theoretic nature, I mean, which is like type 3 theory and so on. So it's clear that somehow one should bring in, you know, all what one knows, of course, about non-commutative geometry and about these things. One should bring it to bear to finish it, I mean, to justify the formula. But I view it really, you know, as some sort of gem, this example, as a motivation to say that, you know, to confine geometry as we do confine it to very, very simple examples where you have local charts and so on, where everything is child play, okay? I mean, this is wrong, and we have to go to spaces which are much more tricky, but then you need to show examples, you know, which show you what you will attain when you've done that. And obviously here, I mean, it's completely clear-cut. I mean, on Thursday I will give many other examples, but they are not as tantalizing as this one, of course. Okay.
Remind you again that the next final lecture on Thursday at 4 o'clock.
This will be the introduction.